So today we're going to look at the vacuum triaxial and plane strain testing of some dry sand samples, kind of an introduction to strength testing. Our triaxial sample will be a cylindrical sample with initial height h0, initial diameter of course, giving us an initial area a0, and we're going to build the triaxial specimen to a low density. We're going to try to build it as gently as we can. The less energy we impart to it as we build it, the lower the density and the higher the void ratio we can build a dry sample. Instead of putting the specimen in a chamber and applying external pressure to generate confining stress, sigma 3 prime, we're going to actually test the specimen out in the atmospheric pressure on the outside, but we're going to apply negative pore pressure. We're going to apply a vacuum to the inside of the specimen. So the pores, there'll be a negative pore pressure. There's no water involved, but inside the pores we're going to have a vacuum, and so our confining stress is going to be equal to atmospheric or zero pressure minus negative U, which gives us a positive effective stress, of course. And we're going to want to track the dry mass, calculate the initial volume based on the dimensions that we get for the specimen, and calculate a mass density. I'll provide you with maximum and minimum densities for this sand, and you can look at what the relative density of the specimen is. Important to point out, there's no water involved, just air in the pores. And so as we shear this specimen and apply a constant vacuum, are we thinking this is a drain test or an undrained test? People talk about those a lot. When you have a specimen like this, as you'll see, we're going to have compression, compressive strains. We're going to have some bulging, but there's nothing about the system to prevent the soil from changing volume. The fluid in the pore space is air, which is very compressible, so even if we had closed a valve somewhere or something, the specimen can change volume. So this is really a drained test, but it's a drained test where we're not measuring the volume change. And in fact, we're going to make an assumption during the data processing as if there wasn't any volume change going on. For constructing the triaxial vacuum test, we're going to build the specimen on a base cap that has a drainage line built into it. You can see the small tube connecting to a larger tube that connects to this sintered bronze stone, which is set into the cap. That's how we're going to have access to the internal pressures. And in many triaxial tests, that would be the pore pressure. This is going to be a dry specimen, and we're actually going to be applying the confinement, again, with vacuum that we apply through this drain line. Before we can build the specimen, it's a good idea to take some initial measurements. One of those is to use a reference height standard. So this lucite cylinder has a measured height of 151.30 millimeters. If we place that on the cap that we're going to use, and we put the top cap on that we plan to use, we can put that whole assembly underneath a precise dial gauge, center it so we can have a good average value, and we're going to read some number off of this dial gauge, which is looks like about 8.39 at the moment in this example. That 8.39 doesn't represent anything by itself, but it's a reference measure. What we're going to do later, after we've replaced the cylinder with our sand specimen that's about the same height, we can put the whole system back under the dial gauge, take another reading, and the difference in those readings will tell us the difference in height between this known standard and our specimen. This gives us a lot more precision than we'd have if we just held up a ruler or calipers or something like that on the system. So that's one of the early reference readings we would take. The other one, we're going to have a membrane. This latex membrane is going to seal around the sand grains, make sure that the pressure outside the membrane can be maintained different from the pressure inside. That's how we're going to have effective stress on the sand. And so we need to know actually what the thickness of this membrane is. So we're going to fold it into 8 layers. And while the system is set up like this, it's convenient to just slide those 8 layers underneath the dial gauge. Now we have a different reading. Of course, the system is taller, and so we can take this reading, subtract the 8.39, divide by 8, and that will give us a good measure of the average thickness of this latex membrane. And there's a space on the data form for that. It should be filled out for you for your specimen. So once we have those initial measurements, we want to take the system back to the table, and we're not going to need the top cap for a little while. We shouldn't need the reference cylinder at all for this test anymore. We need to seal the membrane around the bottom cap. We're going to do that. I want to make sure it's just one layer, but that it's all the way down. And then we're going to seal that on with O-rings, Bunan, essentially rubber O-rings. We're going to have an expander for that. Stretch the O-ring on. And then we're going to slip that around the system so that the O-ring is stretched. It's pulling the membrane tight against the cap, and again, that's going to be a seal that ensures we can have different pressures between the outside and the inside of the sand sample. I'm going to put on 2 here just for good luck. It's more of a superstition than anything else. There's no real reason we need more than 1, but all right, great. And now we want to create that cylindrical specimen above the base cap inside this membrane. And the way we get a nice cylindrical specimen is to build it inside of a cylindrical mold. So this is an aluminum mold. It comes in 2 halves, a split mold. It also has a vacuum port, and it has a porous lining. And so what we're going to do while we're building the specimen, we're going to apply a vacuum to the inside of the mold. That's going to pull the membrane out tight against the wall of this mold, make sure it's a nice cylinder, build the sand specimen inside, and then apply some confining stress before we take the mold apart again. So to put this on, we're going to slide this here. Hold it over and down, slip on the other half. I'm pulling up on this while I do this so that I don't pinch the membrane between the 2 halves. And then we have 4 bolts that we need to apply. So there's really two separate vacuums we're using in this experiment. One is going to be to help us build a nice cylindrical specimen. That's a vacuum on the mold, the inside of the mold. And then the actual confining stress during the experiment is also going to be applied with vacuum from a vacuum pump. I'm working in a different room, so we have a nice quiet environment for this. So I'm running a vacuum line in from across the hall. All right. So once those are tight, I already have the vacuum applied to the split mold. I can pull this, stretch it up, pull it over and down, And what happens is, even though the membrane is slightly undersized, it's a little bit smaller than we want the specimen to be, so it's a little bit stretched out against the wall of the mold, and I can feel that it's tight there. So we have a nice seal at the base, and we're ready to build the specimen. For this specimen, we want to make it as loose as we can, reasonably. So we're going to use a technique called zero fall height pluviation. And essentially what we're going to do is use a cylinder that's slightly smaller than the specimen, that has a screened opening on the bottom. We're going to place that all the way down to the bottom of the cap there before we start. We're going to take our sand. We'll have weighed the mass of this sand first. And we're going to pour the sand into that inner cylinder. It doesn't really matter how fast or slow we pour this in, because what we're going to do to create the low density is to pull that screen up very gradually, very slowly, so that the sample can settle through the screen without falling a significant distance. So sand comes right to the top here. And again, it doesn't really matter at this point what the density of the soil in this cylinder is, but we're going to pull this out very slowly. Move it up to the front while we do that. And of course, as long as the mesh is fine enough, the soil is going to fall through, but it's going to fall immediately onto sand grains that are underneath it, as long as I don't go too fast. And of course, the grains will also fall to the sides a little bit, because this cylinder isn't quite as large as the mold. If I wanted an even looser specimen at a lower density, I could probably do that by getting a cylinder that was just slightly smaller than the mold itself, so that the soil wouldn't have to roll down that slope toward the edges at all to reach its final fabric, right? And basically just pulling a screen up through the soil so that it gets deposited with as little energy as possible. That's our goal here. Takes a little while, but we're getting there. All right. Tap it a little bit. Okay. We're going to end up with a surface that's not quite flat. It's not going to completely fill the cross section of the specimen, so I'm going to take a small wrench here. You could use a screwdriver or a pencil. Again, I want to apply as little energy as I can, and I probably should just recognize that in shifting this sand, I'm probably densifying the sand right at the top cap a little bit. Okay. Now that shouldn't affect our strength measurements very much, because the soil that's right against the top cap and right against the bottom cap are protected from shearing anyway in a compression test. So we might have some small effect on the measured density, but shouldn't be a big deal. So before I put the top cap on, I'm going to put what's going to be the O-ring for the top cap over the top. That will be handy in a few minutes. Okay, and now without vibration, I want to place the top cap down onto the surface and not shift it hardly at all at this point. Now we can see pretty clearly this is not level at this point, so how do we get a nice level specimen? We want to make sure the top platen and bottom platen are parallel, so that our cylinder is a right circular cylinder. And what we're going to do is take a bullseye level or a bubble level, and we're not interested in getting the top cap perfectly horizontal in the gravitational field, we want it to be equally unlevel as the bottom, or the table, or the floor that you're working on. So I'm setting it down here, I'm gauging where the bubble is, and we want to match that on our top cap. That's actually not too bad right there. So I need to tip that edge down a little bit to make them level. All right. So now we want to apply additional vacuum to the inside of the specimen. I think before we do that, though, we would like to roll up the membrane and seal it. So I'm going to push down with gentle but steady force on the top cap, because I don't want there to be vibrations. I just want to pull this membrane up while the cap can't move. That's my goal. And especially while I roll up the O-ring, because that can snap on there. I want that cap to be nice and steady and not flying around, because I took some time to get it level there, right? Okay, so now we have a sealed membrane. We still have vacuum on the mold holding the sample to be round. We still have no vacuum on the inside of the specimen. So what we're going to do is bring over a vacuum regulator. And I'm going to plug that into the vacuum source as well. And this is like a pressure regulator, except it works sort of in the other direction, right? So I can set on this regulator what vacuum I want to have. If this is indicating 12 inches of mercury at the moment. Inches of mercury, for some reason, is still the standard unit of vacuum for a lot of things. It's kind of old-fashioned when people use mercury manometers, but that's fine. We're going to use that and we can convert it later. Each test may be run at a slightly different confining stress. The one thing we want to be sure of is not to over-consolidate the specimen. So I'm putting on a lowish value of confining stress for now, and we'll raise it up to the value that we want to shear at. So I have the other end of the tube that's going into the base cap, remember, through that bottom porous stone, and I'm applying that to the vacuum regulator. And now I have sort of dueling vacuums. I have vacuum in the pore space between the dry pores of the sand, and I know what that is. That's actually about 11 inches of mercury. And I have sort of probably a larger vacuum still pulling the membrane out against the mold. But now that we have some confining stress, we can release the vacuum that's on the mold. So we'll do that just by unplugging it from the source. We can't see anything happen because it's within the mold, but as long as we're confident that we have vacuum going to the inside of the specimen, we believe it should be okay to take apart the mold. If we forgot to put the vacuum on the inside first, we would be disappointed, because when we took the mold apart and took the two halves of it apart, basically we would have a bag of dry sand that would slump and fall over onto the tabletop. So you might ask me sometime how I know that. I've done this a few times. You manage to make every mistake at least once, but hopefully not this time. So we take out the 4 screws. And then we'll have a specimen. Not quite ready to test, but we'll have a specimen. So here we go. I'm just going to separate these two halves. Oh yeah, that looks good. So see the O-ring here at the top. I'm going to roll it down a little bit just to get it away from the edge. And we've got 2 at the bottom still. That's great. So, and I'm going to roll this down out of the way. So, 11 inches of mercury is about a third of an atmosphere, maybe 30 kPa. So this is not a particularly delicate specimen. It's a dry sand. It's under significant effective stress, so we don't have to worry about being too delicate with it now. What we will do is put it back under the top cap. I'm going to stay slightly off to the side of the center because there's a little dimple there, but this reading now looks like it's about 14.94 perhaps. I'm at a bad angle there. We're going to take the difference between that reading and that initial reading we took with the dummy specimen, and we'll be able to calculate precisely what the height of our specimen is. It looks like our specimen is a little bit taller than the reference specimen, okay? But with each test, that's going to be a different number. And so that's going to allow us to precisely calculate the height of the specimen, H0. Now we can move the specimen again onto the tabletop. We're going to do one more measurement because we need to know the initial diameter to calculate the area. And there's a couple ways you could do that. If you had calipers, you could measure the diameter in one place, and another place, and another place. They'd all be slightly different, probably. And some of that is because there'd be a slight variation with height due to the mold, but there would also be a variation because the mold is not perfectly circular. And so you'd want to take a bunch of readings and average them in order to get a diameter. Another alternative is to use this ingenious little thing, which has been around for a while. It's called a pi tape, P-I. This one say that? Yes, it does. So pi tapes are clever in that they are flexible rulers, essentially. They have divisions. This one is in inches, but it measures to the thousandth of an inch. And the way that it can do that is it has a main scale. There's a main scale on this top major part of the system. And then it has a vernier scale, vernier caliper scale on this little dog leg here. And when you wrap it around something that's approximately round, and when you get it level, which is also important, on the main scale you can read what the diameter is to the nearest 25 thousandths. And then you can look on the vernier to where marks on that dog leg match up with marks on the upper scale, and you can read to the nearest thousandth of an inch. So this particular reading is giving me 2.804 inches. So that's the diameter there. Now, these are interesting devices in that there's always some measurement error with almost any measurement you take, but it's not always random. So you don't want to take multiple measurements in the same place and then take the average, because there's a very one-sided bias here. If you get this caliper or this pi tape not level, then you're not really around the circumference, right? You're not wrapped around the circumference. You are measuring some sort of an oval, right, at an angle. So if you take a few measurements in a row, you always take the smallest value at a given elevation. So typically I recommend that we take a value up here in the middle of the top third, another reading in the very middle of the specimen, and another reading in the middle of the bottom third, say. And they'll be slightly different. Then we can average those values to give us an average diameter of the specimen. And what's nice about a pi tape is if our sample is slightly elliptical, what the pi tape gives us is the diameter of the circle with the same circumference. And that's basically what we want, is a nice average diameter. Whereas if we had a calipers and we happened to measure the long axis of the ellipse, that would be an error, assuming it was a circle. Okay, and of course the way it does that, it just factors in a value of pi. It's measuring the circumference pi d, and you divide by pi and it gives you the diameter. So, if you get the chance sometime, you'll know how a pi tape works. What diameter is that we've just measured? It's the diameter of the specimen, but it's on the outside of the membrane. The membrane is not sand. So really what we want is the diameter of the sand specimen. So remember at the beginning we measured the thickness of the membrane. So we want to take our calculated diameter and subtract 2 times the thickness in order to get the diameter of the sand itself. So that's what goes into measuring the initial cross-sectional area and the initial volume when you multiply it by the initial height. So we're about ready to test the loose or low density triaxial specimen. Now we're going to pick it up, place it over here on the testing frame. This is a venerable old constant rate of deformation frame, which is actually really good for this sort of a test. And I'm putting this extra top cap on that has a steel ball bearing, stainless steel ball bearing that fits in the top. That's going to be the interface between the sample and the load cell. We'll talk about that in a minute. Just some details on how the frame works. It's a mechanical system, gear-based, and so there's a total of 25 different rates at which the gear system can rotate based on combinations of these 2 gears and other sizes up here. And then there's another factor of 6 that we can go to with a separate independent gear system here. So I've selected gears here that will deform the table at a rate of 0.1 inches per minute for this test. And the rate of deformation for a clay could be important in terms of the strength for strain rate effects and things like that. But for a sand we wouldn't expect it will make much difference. At that relatively slow rate we could get thousands of data points for our stress strain curve, but we will not do that. We'll back off and take far less. The data we're going to take includes the load, which again is the deviator load, the isotropic confining stress in all directions, again, is supplied by the vacuum. So we want to set that vacuum regulator to the value that we want. And for these tests, typically that's going to be around 1/2 an atmosphere. They'll vary a little bit from test to test, so we'll need to make sure you have the right value for your test. The other piece of instrumentation is this linear variable differential transformer, or LVDT. And that's a displacement measuring device. We'll talk about how these different instruments work in a future lab or lecture. But they're both electronic devices, so they're being powered and calibrated by a signal conditioner, so we can have the calibration that we want, and then the signal conditioner converts the signal to a DC voltage, which makes it easy to record on a computer. So we'll start the data file first to start acquiring data, and we'll do that before the machine is on and while this ball is still not quite in contact with the specimen. So the initial part of the data file will show the case of no load on the specimen, deviator load, and no movement of the LVDT. Then we'll start the table moving, start the machine moving, And at that point, the table will move, so the LVDT will record displacement, but there still won't be any load. So the next phase after that will be suddenly, once the table has lifted the specimen up against the load cell, we'll start to see load. And that is the point at which the shearing actually begins. So the LVDT value that represents zero strain is immediately before that contact, or at that contact when we first see load. So when you're looking at your data file, you don't want to start displacement measurements based on the beginning reading of the LVDT, because we don't even have contact yet, right? We want a good sense for what the zero reading is. That's why we do this. All right, so we're going to start it up. Put it in forward gear. The motor's running, but the table's not moving because I haven't engaged the clutch yet. Here goes the clutch. Okay. Both wheels are turning. That means the table is moving up. I still don't have contact yet, but it's very close. It's important to have the specimen centered under the load cell so that we don't get eccentric loading of our cylinder. If we do that, we'll probably see it in form of the sample tipping over or bending or something like that. So we have load now. We're getting some strain, small strains, nothing visible in terms of the deformed shape. So I'm going to let this run. The whole test, if it's going 0.1 inches per minute, that's a little over 1% per minute, I think. So I'm going to stop the video and we'll check in on it again when it's up at sort of medium strain. So this is the loose triaxial sample, further along in the test, about 8% strain. 7.5 to 8. And if we zoom in a little bit, we're going to look at the shape of the specimen itself. You can see that now that the sample is 7 to 8% shorter, of course the shape is going to change. We're getting a deformed shape where as we squeeze the sample down, the sand is getting larger in diameter, the specimen is getting larger in diameter, but not uniformly. It's happening mostly in the center regions of the sample, the center maybe third to half of the sample. And so we have to recognize that as the diameter changes of the part of the soil that's shearing, the cross-sectional area is changing. And so we're going to need to reflect that in the way we reduce the data and make an area correction. The other thing I didn't talk about much was the ball bearing at the top. Why put a ball bearing in there? By doing that, we ensure that there's no transfer of moment from the load cell to the sample. If we did have two flat surfaces together, then we could have a pretty significant moment there. And the way we analyze the test assumes there is no moment. So it's good to include something that can't carry that moment so that it fits the conditions of our data reduction. The byproduct of that is if we do have a tendency to create moment, instead of moment we get rotation, right? The top cap will rotate, and that's really not part of the condition either, but at least we could see that. We can't see the moments if they were to develop. And here we are near the end of the loose triaxial test specimen. You can see the bulging is continued. It's not happening at the top and bottom caps because, again, those regions are protected by the caps. We can't have shear planes that go through them because the caps are in the way, and so it's the center portion that deforms more. So any volume changes actually are not really going to be uniformly distributed either, although we assume that is the case. Finally, we are getting rotation of the top cap. It's actually tilting, the top cap's tilting away from you. It's probably a little hard to see. But this often happens at very large strains, where some imperfection or misalignment or something is sort of emphasized toward the end of the test. And so beyond a certain point, the geometry isn't really representative or easy to calculate stresses for. But fortunately, this is well beyond the peak stresses or the strength. And so sometimes it'll show up a little strangely in the stress-strain curve at very large strains. But essentially a bulging failure for this loose triaxial specimen. To test a plane strain condition on the sand sample, we have to build a different geometry specimen. So we're going to have to build a rectangular prismatic sample, so that we can distinguish between the two horizontal directions, right? We're going to prevent strain and allow deviator stress in one of the two horizontal directions. And we'll see how that works in the lab today. So that's requiring a different mold, a different system. We're also going to be intentionally building this plane strain sample to a relatively high initial density for comparison with the triaxial sample. And so rather than building it very delicately to allow this kind of very high void ratio metastable structure, we're going to want to apply a lot of vibrational energy in a series of layers to develop this lower void ratio or high density level. So beyond that, the tests are kind of similar in terms of what we measure. We're going to have load measurements vertically. These are going to be compression tests. And we're going to measure a load, and maybe that's P, right? But we want to think about that in terms of stresses. So it's a sigma deviator stress that's being generated due to this load. And then we're going to measure displacements. And the one measurement we're going to have is the fact that if this was the initial height of the specimen, at some future point, I'm exaggerating, we're going to have a short specimen. So there's going to be some delta H here. And our axial strain, of course, is going to be delta H over H naught. We're always going back to H naught, engineering strain, right? So that's the strain we're going to plot. The deviator stress, of course, let's just call it sigma d, is going to be equal to that load that we measure over the cross-sectional area. And that's going to be equal to 2 times the shear stress tau, right? So the one other thing we have to talk about is the fact that this area doesn't remain constant at the initial value. So, and this is true for the triaxial test and the plane strain test. I'm talking about it now, but it applies to both. We do something which isn't technically correct. We talked about the fact that these are actually drain tests in which there is volume change, but we make a constant volume assumption. And then we make an even worse assumption, which is that as either of the specimens, triaxial or plane strain, deform as they are compressed and they get shorter, we're going to assume that the geometry of the specimen remains either a right circular cylinder in the case of the triaxial specimen, or a right rectangular prism in the case of the plane strain specimen. So we're going to basically be saying, since it's constant volume, that the initial height times the initial area remains equal to the current height times the current area, because they're equal to the same volume all the time, right? throughout the test. And so basically we call this a corrected area, A sub C. And at every stage along the test, as the sample gets progressively shorter, H becomes shorter and shorter, this corrected area gets larger and larger, and it does so satisfying this condition. Now we're going to see in the tests that we perform that neither of these are particularly good assumptions, about it remaining a right circular cylinder, or it's a little harder to see the constant volume problem, but we know there's volume changes going on. But this is going to be important because it's this corrected area that shows up in our calculation of deviator stress throughout the test. So the order in which we're going to calculate things and reduce the data is we look at the delta H to calculate the new height and the strain, and then once we have that information we can calculate the new area, and then we can use that new area to calculate the deviator stress at any given time. And of course, the deviator stress, even though it looks like the vertical stress, sigma 1, it's not. It's a deviator stress. That's one reason I want to call it that. If you want to know sigma 1, that's equal to sigma 3 plus the deviator stress, right? And in this case, sigma 3 is the vacuum confinement, and we're measuring or calculating the deviator stress through what we measure, so we can figure out what sigma 1 is at any given time. And that's how we'll be processing the data from both of these tests. The other type of specimen I'd like to demonstrate is a plane strain compression sample on the same sand. But we're instead of building a cylindrical sample, like we did for the first triaxial sample, we're going to need to build a rectangular prism specimen in order to be able to impose those plane strain conditions. So that means we need to have caps that have a rectangular plan area, top and bottom caps. They're both going to have drain lines. We'll talk about why in a little bit, but it's hard to seal a membrane around a square surface, so these caps transform or flare down into a large diameter round cap at the bottom, and that's where we're going to seal the O-rings. So the membranes are quite large. Now the process is very similar to building the reconstituted triaxial sand specimen, in that we would normally start by having a reference height or a reference block in there of a known height, putting the system together, measuring under the dial gauge what the reference reading is, so that once we have a soil specimen in there we can compare it to know what the initial height is very precisely. And also we would want to measure the thickness of the membrane in the same way. We don't need to do that again as part of the video, but then we need to get this membrane onto the cap. That can be a little tricky because the cap has corners. We'd like to not tear the membrane. We need to put a large diameter O-ring onto this sample, and the easiest way to do that is from the drainage line end. So put that O-ring on. Make sure it's over the membrane everywhere, and that'll help keep the vacuum pressure inside the specimen separate from the atmospheric pressure here in the room. Alright, and so now we have a similar sort of a mold. It doesn't come into two separate halves. Instead it has a hinge in the back corner. So we're going to place that mold. Again, I want to pull up on the membrane so as to not pinch it in the mold. A little trickier with this one. There we go. And now there's only 2 bolts for it. But again, this red line is a drain line or a vacuum line to the mold. So again, the mold is lined with a porous material. So when we apply vacuum to that inner surface, the vacuum can pull the membrane up tight into a regular rectangular prism, right? We don't want a specimen that's varying in cross section. That would make the data interpretation very confusing. So here we go. We're gonna just lower down the membrane. Initially, we don't have any vacuum yet, but once we do, here, I can hear it hissing. A little bit of a leak somewhere. This rectangular mold is more difficult to work with and not have leaks, but this is actually pretty good. Not going to take a whole lot of adjustment. We want a nice smooth surface, and as you can imagine, when you try to put a membrane into a square corner, the membrane wants to round a little bit, and the vacuum is trying to pull it out into a more square shape. But we'll have to adjust for the fact that, especially once we take the mold off, we're going to have round corners, and we're going to have to account for those. So looks like the biggest radius is on this hinge corner, and there's not a whole lot I can do about that. So here we go. We have a mold with membrane in it. Again, I can hear a slight leakage, but as long as it's holding the membrane in place, that's okay with us. So, making a prismatic sample is one of the things we're doing differently. The other is we want to build a relatively high density sample in comparison to the triaxial one. So with the triaxial sample, we kind of very carefully put the mesh with the cylinder at the bottom. We wanted to impart as little energy as we could while we built the specimen. And so if you want the opposite, if you want a very dense specimen, as you might guess, you want to impart a lot of energy. So we're going to actually build the specimen in a few layers, and along the way we're going to apply a lot of energy. You'd want to have the mass of the beaker with the sand, and probably good to have a funnel so you don't spill, because we're going to measure the sand that's left over at the end and subtract in order to tell us how much sand is in the specimen. So that's about 1/3 full. And the best energy to apply for densification is dynamic energy or cyclic energy, vibrational energy. So this is going to get a little bit loud, but we want to basically shake the sand particles into a dense configuration. Okay, so that's layer 1. Sometimes the vibration loosens up the mold a little bit. Good to double check that. That's fine. Good. Now we'll do the last layer. We don't want to go all the way to the top because it's important that the cap fit down into the mold. And once again, we can level out sort of a ridge in the middle here. So we'll level that out. Not concerned with shearing. If anything, shearing a dense specimen actually might make it a little looser, right? But that's all right. And we are about ready to put the top cap on. So, whoops, this is the wrong, don't want it on there. Get the O-ring ready for the top cap. Too many cables, too many tubes. Okay, so we're gonna make these line up. And make sure we have good contact with the sand. Make sure the cap fits down into the mold and doesn't bottom out on the shoulder that you can see along the sides there. Okay. We have the same concerns about levelness. So we're going to use our bubble level again, bullseye level. Make sure things are clean here. Not actually level, or parallel, I should say. This needs to be over a little bit. So I'm actually shearing the soil, pushing it as I push down to adjust and get the cap. Yeah, that's pretty good. I need this side down a little. That's a little harder. Yeah. Okay, we're going to have to check that levelness again after we get the O-ring on, because sealing the O-ring on here is always a bit of a disruptive process. So that's good for now. Just like with the triaxial sample, we want to hold the cap in place while we bring the membrane up. And we'll bring it all the way to the top. Get all the wrinkles out, hopefully. You can always fold it back down again, but we want it up high to get the O-ring on and get it sealed. This usually results in some loss of levelness, but we'll see in a minute. Okay. Oh, pretty good. Pretty good still. Wow. Great. So now we have a rectangular prism that we've applied a lot of vibrational energy to. It should be considerably denser in terms of the mass density than the triaxial sample. And of course there's nothing that would prevent us from building a loose plane strain specimen, right? Or a dense triaxial specimen. And so in fact we have data for all four combinations. Different groups will be looking at different combinations to see what the effect is both on the stress strain curve and the mode of deformation that we see visually when we run the tests. So we're about ready for applying vacuum to this specimen, and follow the right tube. Yes, that's coming from here. So this is the base cap, so I'm going to bring my source of vacuum over, vacuum regulator. Slide this a little bit, make a little space. For some reason that's very awkwardly positioned there. All right, there we go. And which one was it again? This one. Okay, so we're gonna plug this in here so that we're applying vacuum now to the internal part of the specimen. And you know what? I'm going to plug it in the other one, I think. Okay. And we also want to put a vacuum regulator into the end, coming out the top. Right? This is a superstition of mine. These samples are more prone to leakage than the triaxial samples. There's so many more corners and things involved. So now that we have vacuum on the inside of the specimen, we can take the mold apart and see how it's looking. Okay, open the door here, as it were. Okay, and the mold is still under vacuum, so we'll pull that off. That's good. And voila, a specimen that is essentially rectangular prism. So we have a narrow dimension and a wide dimension, and of course, as we discussed a little bit, these corners, when we're pulling the membrane in with a vacuum, especially, that's going to pull these into rounded corners, and so to get a really good measurement of the cross-sectional area across the horizontal prism, we're going to need to account for those corners as well. So the volume measurements are relatively straightforward. The height measurement is exactly like we did with the triaxial specimen. We're going to put the whole system underneath the dial gauge and look at the difference or the change in height relative to when we had a known reference between the two caps, so that's pretty straightforward. Measuring the cross-section based on the rectangle, of course, is relatively straightforward with a dial calipers. This is a digital calipers, right? We could put that across the specimen in a few places, read off values. Okay, so that's what we do. We want to do that in a few places, again with height, because it could change a little bit. You want to check and make sure that you're relatively level, right? And we can do that for the broad length or the narrow length. So the length times the width then is going to give us the pure rectangle, and then we do want to account for those corners. And so the way we measure those corners is a little different. This is a rigid steel right angle, and the two sides would meet at a right angle there. And so by holding up a ruler or this calipers, I can measure, using the inside jaws here, approximately what is the radius of that curvature, of that corner. Okay, so that is, in terms of this t-square, that's saying what is the distance from one of the rigid sides, flat sides, to, how far along the other flat side do I have to go to reach contact with the membrane. And in this case it's about 800ths of an inch. And all the four corners will be different. And so we'll have to measure the cross-sectional area of the specimen as a whole, we're going to multiply the width times the length, but then we have to subtract little squares that are of length of the radius. So we're taking out a square from each corner, and then we're adding back in a quarter of a circle that has the dimension of that radius. So we'll go over that on the board a little later, but it's kind of an extra detail we need to do when we go to measure the density for this specimen, because it's not able to occupy that full length times width. So we have our dense plane strain specimen here in the device, and it's set up very similarly. It's important to have it centered. We have the load cell above on the crossbar. We have a small gap still between the sample and the load cell. The LVDT is here. Again, it's going to measure the displacement of the table as a function of time. Of course, that table is pushing the sample up against the load cell to run the test. But there's one more very important feature in a plane strain test, and that is how do we enforce those conditions of plane strain. And that's what we need. This system, there's 2 rigid platens and 4 tie rods that hold them together. And we're going to put those across the small vertical surfaces to prevent the sample from straining in that lateral direction. So by putting these platens on, we're defining what's going to be the sigma 2 direction versus the sigma 3 direction. So, and I've put a little bit of vacuum grease, a lubricant, on the faces of these so that we don't have a lot of friction with the membrane. But this is going to fit here and here. It's 2 of them. 3, 4. There we go. So basically we're clamping the specimen in this horizontal direction so that it can't expand toward the camera or away from the camera toward the whiteboard behind the system here. It can still bulge horizontally, but it has to bulge either to the left or to the right. And in this system, these end platens are made of clear lucite so that we can see what's happening a little bit within the specimen while the test is going on. That doesn't need to be plastic, and in fact we have other systems here in the lab that are metal, and on which these tie rods have strain gauges. So in order to prevent that strain in the epsilon 2 direction, right, the sample wants to deform laterally when you're squeezing it, so it tends to pull and put these 4 tie rods into tension. And so if you have strain gauges on all of those, you can measure the force with which the sample's trying to do that, and you can calculate a horizontal deviator stress, sigma 2 minus sigma 3, and you can use that to calculate sigma 2. This system isn't set up to do that, so we won't have that data, but you certainly can. And we want these plates on kind of snug. If they're too loose, they just slide down on the grease. But we also don't want to pre-squeeze the specimen much in the epsilon 2 direction either. So this looks pretty good. Alright, so we're going to bring the specimen up a little closer, and we think it's level, and we think it's centered. Both of those are important. I think actually it needs to go back. Come forward a little bit. This needs to go back, and this needs to come forward. As soon as I said it was centered, I noticed it wasn't centered. So I don't know what happened there, but these plane strain specimens are very narrow in this direction, and so they're very sensitive to being not centered or not straight, and we might see that as we run this one. We'll see. So think about what you're going to expect from a dense sand in plane strain. What sort of mode of deformation? Now we know it's plane strain, so the bulging is only going to happen again to the left and to the right, but do we think it's going to be a generalized bulging failure or a discrete failure plane with localization or something in between? Hopefully it's not going to be tipping because it's not centered. Alright, oh, you can even see where that squeezing of the grease has actually highlighted the color change here. I think the darker color is where we have contact, good contact already between the membrane and the plate and the grease. Oh, and I'm noticing here at the bottom, I don't want the tie rods touching the caps either, so I just adjusted that. Alright, we're going to shear it at the same rate. We want to check our confining stress, make sure it's what we want. Oh, and I didn't mention, why do I have a second gauge? It's attached to the top. So if I had a slow leak in the system or a minor leak, I might think I was applying 50 kPa of vacuum to the bottom, or I might be applying 50 kPa of vacuum to the bottom, but up at the top I might only be measuring 37 or 42 or something like that, and that would be a good indication that somewhere at a corner or somewhere, maybe at an O-ring seal, there was a leak. But I'm seeing good agreement between these two, so I think we're in good shape. This is now tipping a little bit. Need to push this tie rod over a little bit so it doesn't touch over here. Okay. Alright, here we go. We have the data file running. We're going to engage the motor. Make sure we're in the right gears. We're going to be deforming at the same strain rate as the previous triaxial sample. And I'm going to engage the clutch. And if I touch this, you can see the ball bearing moves freely. So we're not in contact quite yet. That stays centered. We're very close. Still a little movement. That's fine. Very close now. I can still spin the ball easily, but it doesn't really go anywhere, so loads are going to pick up very quickly. And again, we'll look at this early loading. It's probably a little harder to see the bulging with these plates in the way, but we may be able to see something on this surface. This broad surface is the one that can bulge, right? Because here we have the constraint. You can actually hear grains grinding either against each other or the plate caps. It's kind of a Rice Krispie sound. We haven't gone that far yet, and yet I believe we have localization occurring. There's a failure plane developing already. Of course, it's on the side where you can't see it. So I'm going to pause the test for a moment by pulling out the clutch and bring over the camera so you can see. So excuse the shaky cinematography here, but this is on the right side. See down behind the LVDT post, there's a horizontal line across about an inch up from the bottom of the specimen there. That's the failure plane daylighting toward the bottom. Now if we move around to the side, do we see any evidence of that through the plate? There's a little bit. You can see that it sticks out about an inch above the bottom cap on the right side. It's starting to daylight there. And if the failure plane is there, it must be running steeply up to the left, probably right up to the corner with the top cap. It's kind of hard to see that at this point, but we'll track that, and when we take the plates off at the end, it'll be very obvious where that is. So we're resuming with the dense resuming with the dense plane strain test, and if we see a localized failure plane, we've already have failure, right? And so we are just continuing to generate shear displacements, but they're all focused on one relatively narrow plane across the specimen. So we have essentially almost a rigid block to the lower left and a rigid block to the upper right, where there isn't any further volume change happening, and all the action and all the shear and all the volumetric strain is happening across that narrow zone, that localized failure plane. Okay. So we're going to continue for just another moment or two, and then we'll take the plates off and you'll get a really good look at how that shear band occurs. It's right up at the top cap on the left and cutting down steeply to slightly above the cap over on the right side. So as you're processing the data, what's that going to look like, do you think? You're going to have a ductile failure or a brittle failure with a sharp peak and a drop in shear stress. We'll see when you process the data. And we'll compare between the different combinations of high and low density and triaxial and plane strain, how those different factors affect the modes that you get. Okay, so this is way past failure, so we're going to pull the plug and turn it off, and we'll be able to see a lot better once we take these end plates off what was happening. It's hard enough to see in person through the end plates, but with the camera I'm sure that's not gonna work so well. So let's get the plates off. Of course, you can't take the plates off during the test because that's what's enforcing the plane strain conditions. But now that the test is over, we can have a look. I'm just glancing at the vacuum regulator and the gauges, and they are holding steady, so that's good. In your data files, you might notice there is no recording for the pressure, for the confining stress. So that would be a way to probably improve this setup, would be to add that. we're relying on the fact that our vacuum pressures are going to be constant. So we read a value at the beginning and it holds throughout the test. So it's a constant. Sigma 3 is a constant. Well, sigma 3 total is atmospheric pressure pushing on the outside, right? But sigma 3 prime is the vacuum as a minus pore pressure, right? Negative pressure on the inside leads to positive effective stress. So here is our sample, and if we come up close to the cap, you can see better what happened on that right side. Okay. And the membrane itself is very striated here because it also had to deform a lot over a short width. So the shear band runs here. The top cap has actually kind of punched down and the sample has come up next to the top cap on this side, and this is the daylighting failure plane there. So if we take the vertical load away, we can also rotate it and get a better look. Okay. This is a wrinkle that was there from the beginning. Feature. Feature, yes. There was another one over here as well, but yeah. So, distinct localization implies what? Dilation, right? Because once a failure plane shears, if it's dilating, it's becoming looser, all the subsequent deformations are going to focus on that looser plane because now it's become the weakest plane. Right? So, just as theory would suggest, if you build a dense specimen and you test it at not very high confining stress, you're going to see dilative localizing behavior.